Hello, everyone. Welcome to a Spec Toolbox webinar. I'm Marco, product manager at Spec Toolbox, and I'll be hosting this first session. Together with me is Jason McCool, and he'll guide you through the design examples and theory for dowel design of timber buildings for USA. So I'll quickly just share my screen to take you through some of the updates, and then I'll pass on to Jason. Just a sec. So again, hi everyone, and welcome. Before we start, I'll just quickly mention a few sentences about Jason. So Jason is a professional engineer licensed in 16 states throughout the central and western U.S., and he is the owner of Coal Country Engineering in Cabot, Arkansas. He has served in most of the officer roles of the Structural Engineering Associations of Arkansas over the last 13 years. He delivered multiple in-person and online presentations for events such as State of Engineering conferences and served on the editorial board of Structure magazine for 5 years. His primary areas of focus are steel and timber construction, seismic design, and connection design. He is the lead author of Wood Design Guide published by NCSEA. So Jason will take you more about the details of how you can design and use Spec Toolbox for dowel and bolt connections. And at the beginning, I'll just briefly mention who are we, how you can sign up at Spec Toolbox for those who are first time with us. Also, something about the latest and upcoming updates, and something, as I mentioned, in specifics for advanced dowel bolts and design will be taken by Jason, and in the end we'll have some room for Q&A. So at the beginning, who are we? We're Spec Toolbox. Nice to meet you. We're a team of 55 software and structural engineers, and we build software for design of mass timber and connection products mainly. We are started in Australia, then we have been across New Zealand, Europe, UK now, and North America as well. Our main mission is to make innovative products easy to specify. So at the beginning also, would like to mention that firstly, big thanks to our partners that are listed here. So we have a partnership with over 35 product manufacturers across the globe, and also for anyone that are first time with us, would like to test the Pro version of Spec Toolbox, you have ability to reach out to us, and we'll give you 30 days free trial starting whenever you wanted to start with this. And you can also register the app using the link that is shown below. Just also a preview of some of the differences between free and pro and enterprise version. So most of the manual options and also enterprise and collaboration features are available only to pro and enterprise users. So once again, anyone who wants to try, just feel free to reach us with a contact button, or you can also leave your contact in the chat. In terms of the upcoming updates, so just a preview of something that is coming in the next couple of weeks. So also for, in particular for the US context, we worked for panel connections, and in particular for half lap, spline, and butt joint connection, as these connections are some of the most popular for mass timber context. So all of this will be available and possible to design together with all our timber manufacturers, but also all the hardware or screw manufacturers that are available on the platform already. Going further, Jason will take you through the current large dowel bolt module, but we are also working on new UI that is here just as a preview. But just to point out some of the news that and the updates we're working regarding input-output interface, also tabs that will be introduced instead of scrolling options, then a dynamic image will always be on screen, and we'll also have clear outputs with section explanation. So we focused more on readability of the design, and this is first will be started on large dowel bolts in the next couple of weeks. Also, we're introducing a fire module for our member calculation, so for both the CLT floors and walls, and also timber beams and columns. That will be integrated within the current calculators with just adding new modules. So this is something that we worked on in the past few months and will be available as well very soon. The last part of some of the updates that are coming is regarding the CLT shear wall. So with options with multiple floor level calculations, also bracket and product and hold downs will be also as something that will be available for selection and modification. Also dynamic view, and everything will be according to SDPWS from 2021. So this is we're really excited about sharing these updates, and we hope all of this will be useful for all of you looking for new mass timber tools that can improve your design process. So that being said, I'll pass on to Jason.
Hello. All right. Let me get my screen shared here, and we'll get started on this webinar. Okay. Okay. Just starting out with a little navigation and terminology. In the if you've been using the website, the 3D graphic window, you can use the left mouse button to rotate the joint in 3D, and then you can use the right mouse button to pan it, scroll wheel to zoom. Some of the terminology used in the program is a little different than what you'll find in NDS, so just wanted to kind of clarify here. Like the A1 is going to be your spacing along the grain in the row of the fasteners. A2 is your perpendicular to grain distance there between rows, and then you have A3 is going to be your edge distance or end distances on the wood. A4 is edge distances to wood, and then on the steel plate portion, E1 is going to be your end distances left and right, and E2 is going to be your edge distances to the plate. So we'll see that in the live demo. I just wanted to kind of clarify that up front. So we'll start out with some theory about how fasteners are done in NDS. So we use yield limit equations from NDS tables 12.3.1 and B. And here's from NDS Appendix I, showing the different yield modes. So we go over modes 1 in the main member, mode 1 in the side member, mode 2, which only applies to single shear connections, mode 3 in the main member, again only to single shear connections, and then mode 3 in the side, and mode 4, those apply to single and double shear. So this gives us 6 equations for single shear and 4 for double shear. And if you've done any work in NDS, these are probably quite recognizable formulas. But if you're new to NDS or to American design, then this is kind of our basis of fastener design in the US. It gives us the same equations for any cylindrical dowel-like fastener embedded in wood. So bolts, nails, dowels, screws, spikes, anything like that. And addresses the bearing yielding in the wood. It's mode 1 there. Fastener pivoting with localized wood crushing, so there's no bending in the fastener in that one, mode 2. And then fastener yielding with wood bearing yielding, and fastener yielding with wood crushing. It's modes 3 and 4. Those are differentiated by having one plastic hinge in the at each shear plane, or having 2 plastic hinges at each shear plane. Now, the formulas themselves are pretty basic, but they do get a little more complicated once you start adding in all these different terms. So we go over to table 12.3.1b, and that reduction term in each of the equations actually takes on one of three different values depending on the yield mode. And that's based on the angle of loading with respect to grain direction. So if we substitute those in, then that changes up the formulas a little bit here. And then, of course, these K factors here make it quite a bit more complex. So if you've ever written spreadsheets for NDS calcs, this really starts bogging down. But then each of these K factors, you see RE and an RT term, FEM, and that's where those K terms are used, mostly in single shear, and then one over here for double shear. But then the RE is your ratio of wood bearing strengths, or of member bearing strengths, and then RT is the ratio of bearing lengths. And then those bearing strengths for steel is pretty straightforward. For wood, you're going to have a differentiation between parallel to grain and perpendicular to grain. Both are dependent on the specific gravity of the wood species, and then perpendicular to grain also has to account for the diameter of the fastener. And then as we get into combined forces, of course, we're going to be bearing at an angle to grain a lot of times. So then you got to multiply those together, take into account those angles. So it makes for a lot to write spreadsheets or MathCAD worksheets for. So that's one thing I like about Spec Toolbox is it's already accounted for all of this internally, so I don't have to reinvent the wheel. Going on to member limits at the connections. NDS in chapter 11.1.2 says that local stresses also must be considered for multiple fastener joints loaded parallel to grain. So they point you to Appendix E in NDS, which provides one method. They say, others are allowed. You can be an engineer, and if you want to address something else, you're allowed to, but they do point you to this for addressing three specific limit states. One is net section capacity. So it's just your basic tension rupture of a member at a reduced cross section because of holes for bolts or dowels, whatever it is. Then row tear out capacity. So we've gone from tension to a shear only limit here. And basically you're developing that shear plane on each side of the row of fasteners. So you get a shear capacity on each row, and then you sum the rows to get a total. And then group tear out capacity is a combination of tension and shear. If you've ever done any steel connection design, this would be similar to your block shear failure mode in steel connections. And you see you've got your one shear plane on the one row, and then your one shear plane on the last row, and then a tension applied to that area, perpendicular area in between. So those are all addressed automatically in Spec Toolbox, which I also really like. I've used other software before where that was just kind of swept under the rug and just said, you need to check additional failure modes as applicable, but that's already being checked automatically in here. So now looking at a typical bolted joint here, how do we actually, once we get like complicated loads on here in multiple axes, how do we actually come up with that force? So we can come up with the capacity of the screw, bolts or dowels. We can come up with the limit of the member themselves around those fasteners, but how do we come up with the actual forces? So the spec toolbox is going to come up with a bolt force, a resultant force at each fastener. It's going to be taking the horizontal force, the vertical force, and then the moment, and combining those. The shear and axial forces on the joint are distributed equally across all the fasteners. And you can see that just FH is just divided by N, the total number of fasteners. Phi similar. The moment on the joint is distributed based on the joint rotating as a rigid body. So the center of rotation is the bolt group centroid, noted by point C here in these illustrations. And then that bolt radius, R, is just the square root sum of squares of the bolt coordinates. And you can see there the R going to the center of rotation. That resultant force is perpendicular to that radius. And so what's important here is that unlike steel, wood has significantly different properties, parallel to and perpendicular to the grain. So your resistance is changing as the angle changes. So you can see, like in this illustration here, this bolt, the resultant force is almost parallel to grain, whereas this one, it's a lot more perpendicular to grain. So you're going to see a lot different resistances in those two directions. And so under combined loading, each fastener is going to see both a different resultant force and a different capacity. What this means is that the most critical case may not actually be the one with the highest load. You can have a real high load going fully parallel to the grain and not be as critical as a lower load that's acting more perpendicular to grain. But the calculator is going to check each fastener and provide a utilization ratio for each. And now what we'll do is go through a little load derivation so we can just hand verify what spec toolbox is doing. So I've just done a little 4-bolt pattern here, 6 inches across horizontally, 9 inch vertically, with a 1,000-pound vertical load, 2,000-pound horizontal load, and a 5,000 foot-pound moment applied to it. This is 2 plates, one on each side of a wood member, say a brace or something, or a stub cantilever or something, maybe with that moment on there, something like that. But we're going to take that bolt force formula and substitute in our numbers here. Get that R is going to be 5.41 inches in this case, just 3 and 4.5, half of each of those from the centroid. The horizontal force is going to be that 2,000 pounds divided by 4 bolts and 2 shear planes, so 250 pounds at each location. The vertical load of 1,000, similar division there, so 125 pounds equally on all 4 bolts at each shear plane. And then if we take this term here with the summation of the squares of the coordinates, that gets us 117 for this denominator in that moment term. And that's actually one thing I like about spec toolbox is they split out a lot of these intermediate results and show them to you. So if you're hand checking anything in spec toolbox, you can you don't have to go all the way to the end and not come up with the end result and then try and figure out where it's different. They're going to show you values like this intermediate result, so you can kind of see, okay, I made a mistake on one of my coordinates here or something like that. So you don't get all the way to the end and figure out you got a problem. We're going to take that 5,000 pound-foot moment, translate that to 60,000 pound inches for unit consistency, and plug that in, and we'll get the moment portion of the force on each bolt will be 2,774 pounds total. 2 shear planes gets us 1,387 pounds at each location. Then what we'll do is we'll combine these. So the vertical shear force on that joint combined with the vertical component of the moment and the horizontal shear force and the horizontal component of the moment force. We'll square those, combine them, square root some squares, plug those numbers in. We get 1,665 pounds as that max load. That's where everything is combining together, nothing counteracting. Other bolts are going to have different values depending on how those in-plane shears combine or subtract from the moment load. And then we can move this over and plop in the results from a little verification calc I did in Spec Toolbox. And you can see our numbers all match up there with that bolt 2 that has the highest load where everything is adding together. You see, like on bolt 3, it's actually almost exactly counteracting there, and then the other 2 bolts are in between those values. Now, moving on to some of the background on brace connections. The loads are generally going to be along the grain in the brace connection, in the brace member, and then at an angle to the grain in the supporting member, whether that's a beam or a column. So for this connection, I'm going to be using NDS supplement table 5B for the brace member because it's primarily loaded axially. Tear out is always really likely to govern on a brace member because you're primarily loaded in tension or compression, but a lot of times tension is going to be what's governing, especially with holes for bolts. So say for a brace, you're generally assuming pinned ends, so it's going to be uniaxially loaded. As such, it's going to get evenly distributed among fasteners because there is no bending or transverse shear to add or subtract there. So there is a group effect factor, a group action factor that's going to be applied to account for unequal load distribution along the row of each fastener. But otherwise, the forces get distributed equally. That gets taken into account in the adjustments after you come up with your lateral capacity on each fastener. Knife plates are often used with dowels. The dowels can either be flush to the surface or inset and concealed under wood plugs. I've had several where the architect wanted a nice clean look, so the fasteners were all concealed. You can also do that for fire resistance. If you've got a big enough wood section, then you can use a thick plug to provide, say, hour fire rating, as the case may be. Load duration factors like C sub D in ASD or the time effect factor lambda in LRFD, those do not apply to steel plates, so make sure you don't take that increase in load capacity. That just applies to the wood members, not to the steel. And so going into the live demo, what I'm going to do is take a 6 3/4 inch by 7.5 inch Douglas glue lam. This is combination 2 from table 5B, so L2 there. And I'm going to put a 40 kip seismic load on there in tension. Doing this LRFD, so there's no load factor. It's 1.0 load factor under LRFD. And you can see there's my 1/4 inch by 7.5 inch A36 knife plate. I've got that centered in the brace. I've got 1/2 inch diameter A307 dowels at that spacing and transverse gauge and distance shown. And then I've calculated separately the group effect factor at 0.986 and C delta. I'm making sure it's 1.0 by spacing everything out the way I did. So I've got the 5D on my spacing in the row and 6D in between, 7D on the end. So I'm good all there. But one nice thing with Spec Toolbox is it's going to, and I'll show this here in a minute, it'll actually show me the distances that I'm using and what that compares to against the tables in Chapter 12 of NDS for edge distance, end distance, spacing distance, all of that. So we'll jump into this demo, and this is basically the type of joint I'm doing. This is from an old job I did back in 2018. Before I had Spec Toolbox, I had to do this all by hand. So now we'll show what it looks like in Spec Toolbox. So here I am in the app, and I'm going to pick this particular calc. It's going to load it up, and you can see I'm on US. Of course, you have a lot of other options here. And I'm doing imperial units. I've picked SmartLam as a supplier. You can see we got lots of options here. And Doug Fir, and there's the grade that SmartLam provides for that. All of their product catalog, the sizes they produce will come up in here automatically. And then here's that 3D view, so I can rotate that around, pan it around as needed, show that in different section views, which makes some of these dimensions a little clearer compared to the 3D view. And then if I want to keep this 3D view open while I scroll down the page, and that's how it's done right now. Of course, Marco mentioned that's going to probably be changing at some point in the future, but we'll proceed on with this. You can see specific gravity comes in automatically from the Doug Fir. And I've picked a middle steel plate. So you can see middle steel plate. And you can, like I could pick 2, 3, even 4. Of course, I don't have room for that many with this narrow of a member, but I could. And then the steel, the timber side member, that populates automatically when I pick middle steel plate. There's my force that I've put in. I've got 0 for the other forces because it's a brace. Looking here, I'm using NDS. I've got 10-minute duration for the seismic loads, picking LRFD. And then you can see, each of these little green boxes. If you haven't used this before, one thing I really like about Spec Toolbox is they do a pretty good job of giving a lot of educational content. So just here as an example, this is going to give references, ASE 7 and NDS, and delineate the differences between ASE and LRFD in the WID code, show some characteristics of each difference, nice little summary table here. Some of these boxes aren't functional yet in this beta version for this app, but if you've checked out some of the other apps that are not beta, then you've already seen they show like really good, like the vibration calc on the CLT floor module is really good. It's just given a lot of information. You can kind of set a junior engineer loose with some of these calculators and have them just go through all of these little green boxes here to learn exactly how to use the program without, and probably actually get a lot of education if they're new to mass timber. And then tell them, go through all of this and then come back to me with any questions you still have. So, got all of our adjustment factors here for moisture, so you can set dry or wet, and then you get your 1.0 factor here. I've got my time effect factor, lambda, because it's LRFD. My shear reduction factor from chapter 5 of NDS, that's going to populate automatically because it's a GluLam connection. Temperature, there's my geometry, and then I put this in manually here. Moving on, member data, this is just it's gonna automatically subtract out that plate thickness and give me the timber side member thickness. That's going to be L sub S in your Dowel equations. Moving on to the steel plates, I can pick different, stainless or carbon steel, A36. Typically, if I was using like a really thin plate and needed it a little stronger, I could pick a 572, and you can see, it's going to update the yield strength, ultimate strength, and whatnot accordingly. Thickness. Here's my E2. That's my edge distance. So going back over here, that's going to be distance from there to the edge of that plate, which is also the edge of the wood in this case. But those are separate parameters. 1.5, that's going to be my end distance back here to the internal end of the plate. And this 10 here is going to be to the over here in the at the exterior end of the plate, and which doesn't really, I can make that 8 or 6 or whatever, just as long as it's outside of that minimum. Doesn't really change anything on this. For fastener data, I'm doing a even bolt distribution. I could make that like a staggered bolt pattern if I wanted. I'm doing 1/2-inch diameters, doing dowels instead of bolts, so there's no head on those. Bolts, then see it's adding a hex head on there. And then I'm doing 2 rows of 5 bolts each, and user-defined spacing. So I'm picking 2.5 inches along the grain, 3 inches across, 3.5-inch end distance. So that's basically all the input. You can see right now it's flagging this as failing a geometric check. So what I'm going to do is I can come over here and go down here, and you can see it's right now it's showing that as unacceptable, even though it's saying my minimum is 3.5 for getting that 7D requirement for C delta equals 1. Showing I'm right at the minimum, so that's actually just a little rounding issue we got right now in the beta version. So if I put in something insignificant there to bump it up over, you can see that it's reading it now as correctly passing that. But one thing I do like, it's showing me where these spacing and edge distance requirements come from in the code, table 12.5, 1D and B and C and so on. But it's also not just pointing me to where they are in the NDS code, it's also showing me how my actual values compare to that, so I can get a real quick, easy gauge of that. Where am I at exactly the minimum? Where do I have some room, like I could potentially tighten up this bolt group if I needed to? Maybe needed a smaller connection. And that's really everything there, I think. So moving over to the design parameters, it's going to give me some of these intermediate values. There's that sum of squares of distances that I referenced earlier in the load derivation. So I can just kind of check what I'm coming up with as I verify some of these numbers. There's my 2 shear planes, my force. And one thing I really like is the transparency of Spec Toolbox, because it's showing me the formulas. This isn't like all of my Excel spreadsheets that I've done in the past where I'm looking at cell A1 times cell B3 equals D4 or whatever. Nice readable formulas. Down here, I've got the formulas and the results from those formulas, and then a little summary down here. The resultant forces are kind of boring on this display because I don't have any moment or combined loads here, so it's just equally distributed to all of the dowels in this joint. But on the next demo with the moment calculation, that would be quite a bit different on each of those. Fastener results, this is going to give me the more thorough breakdown here of, here's my coordinates, here's the shear force, which is 0 in this case, and horizontal at axial force, and it's 2,000 on each bolt at each shear plane. Of course, I don't have any moments, so my force due to that moment is 0, so my resultant just equals my horizontal load there. 0 angle, it's parallel to the grain. And then here I've got a little summary table of my loads in each direction. So there again, the resultant just equals the horizontal. Yielding resistance. This is where we get into the kind of meat of it here for any kind of dowel fastener. You can see I've got my factors shown there for LRFD. More of those intermediate values when you're back checking against formulas in the book. I've got my RT, my RE, my dowel bearing lengths and strengths, and then that K theta, FE parallel and perpendicular. In this case, FE theta equals FE parallel, of course, because they're all parallel to the grain. Those obnoxious K formulas in the code, I've got the results for that, so I don't have to hand calc those if I want to just check some of these limit states. And then, of course, I've got it divided up by limits, by yield mode here, which is nice, so I can see exactly how each one's comparing. So usually that one's going to always be pretty high. Usually mode 4 is going to be what's governing, and it is here. And so you can see I'm at 95.79%, so right close to maxed out on this connection. If I go up to, going back here though, you can see, I could look at that and say, okay, I'm at almost 96%. Mode 4 is governing that strength of my dowels. Maybe I could, instead of A307, maybe I could go up to like a grade 50 dowel and drop that back down some. Drop this ratio down a little more. But what we're going to find is, in this case, that won't really help me any, because if I go over here to my brittle failure modes, I'm fine on net section for tension, but if I come over here to row tear out capacity, I'm at almost 93% for shear tear out there. And then group tear out, just under what my dowel bearing was. So even if I bump up dowel bearing, it's not going to help me any unless I change some spacings on here to reduce this tear out or increase my tear out capacity. And then timber cross section, don't have any shear, so this is going to be 0. I don't have any bending, so that's going to be 0. I do have some tension, but again, you can see my formula clearly laid out, my factors clearly laid out, and intermediate results, and then at 75%. So basically finishes out that, and then while we're here, just show what if we did like two steel plates on here, so you can see that's going to there. You can see that reduced my wood member thickness, and you can also see it's telling me that I'm failing in either my member or fastener now. Go over to summary. You can see the yielding is where it's failing. It did increase group tear out, but the yielding resistance is where it's really failing at. So I could come in here. Basically, I've got less wood, so that's probably what's driving it here. But, yeah, my mode 4 here went way down. Got cut in half. Mode 3S did as well. Basically, all of these did. But the nice thing is, this lets you explore different options really quickly and easily. I could switch that to a switch that back and okay, well, that's not one. Let me do that right now. Okay, so that was working the other day, but I could switch that to external plates, and the and it would show the plates out here on the side. My member thickness would change to 6 3/4, like this, and then my side member thickness would become the steel plate at 1/4 inch. But anyways, so that would change and let me explore just different options really quickly and easily like that. And then as far as reports, like you can come up here, print summary or detailed report, and just move this over here. So like for this summary report, you can see I already generated this PDF, and just going to give me a nice summary of the go, no-go green lights here, and nice illustration of it, and my limit states. Since this is a seismic brace, I really want a ductile limit state to govern, so I am mode 4 is governing there, so that works. But all of this just on one page, or I can do the detailed report that's like about 11 pages, but that's gonna run through the whole 9 yards here, and there's that. So now we will go back to presentation and set up for the next demo here, which is going to be a little rigid frame moment connection. So I just set up a little kind of maybe a pavilion or something that's wanting to be done out of glulam, CLT roof. So I got a 3-ply CLT roof and some southern pine glulams, 6 3/4 by 24 3/4. And I'm going to be looking at this joint here in the corner. So I picked a location in Mississippi that had adopted, that state adopted IBC 2024, which brings in NDS 2024. And I put some 20 PSF dead load and live load, roof live load on there. That covers my CLT roof, and there's my framing sizes. I picked a glulam grade from table A in the NDS supplement for the column as well, just because bending is the dominant loading on this, so not axial loading, so that's why I picked 20 FV5 SP for my column as well. And then I picked the same size as the beam just because I'm going to have a big connection plate here. So here's my shear and moment diagrams for that from my analysis software. So I get, and I did a rigid joint up here at the ridge as well. So I've got 60 kip feet up there, but I've got 111 kip feet at the eave connection here between the first 1 to 12 sloping roof beam and then the vertical column. 15 kips of shear and 7 kips of compression. So my those brittle failure modes aren't really going to come into play on this because I'm not under tension there. But bending will be the dominant loading here. So there again, I've got my 6 3/4, 24 3/4, 20F V3 glulam roof beam, ASD gravity loading as above. I'm using a 1/4 inch V36 knife plate centered in the brace, centered in the roof beam, not the brace. And I messed up here. This is actually copied over from my brace. I apologize. I am not using 1/2 inch dowels on this one. I am using 3/4 inch dowels. It is still a knife plate in the center though. And on this one, my group action factor is 0.958. And again, it will be CLT equals 1.0. So we will switch back to the spec toolbox, and we'll jump into the Oh, to this calc, you can see I did the same thing. I picked Smart Lamb again, picked Southern Pine this time, um, and you can see I've got the specific gravity updated off of the Southern Pine, and you can see it's if I pick that, that'd be table 5B. This is table 5A for bending. There's my axial load, my shear force. There's my bending moment. So here I picked ASD. A lot of this is going to be the same. There's my member thickness for the wood. And here that dowel bearing strength in the steel, that 87, that's automatic there. Here I'm using 3/4 inch dowels, and I've got 4 rows of 8 of them. You can see that here. And then got those spaced at 3.5 inches along the grain. Got 4-inch end distance, 3 3/8. Basically, I picked that to give me a 6-inch spacing in between rows. So you can see here, I'm passing on the geometric check with my 3/4 inch dowels. So my minimum spacing is increased some on each of those, but I'm still over on each of those. So I'm good there. But you can see I was at 116% under yielding. So I'll need to look at changing that. Go over to design parameters and forces. Here you can see this is a little more variety than the brace. So I can look through here and see, okay, there's my resultant F1. So on this first row, first bolt here, I've got 3,027 pounds. That is the largest resultant force that I see anywhere on here. And we can dig down into that. There's bolt 1, so you can see which number these are referring to. So actually, okay, here we go. 3148 is that one, and that is my max. A little crowded here when you get a lot of them on here, but you can actually see there's the 3148. And if you zoomed in and followed the line, you can see it's actually playing down there. And then this is going to give me the resultants per shear plane for each fastener, and then split it out to there. You can see the vertical load is uniform across everything, and the horizontal is uniform across everything.
I'm sorry, Jason. Not sure if we can hear you. Is it only on my side? Jason, can you hear us? Can you hear me? I'm not sure if your audio is working now. I think you need to unmute yourself or something. No. Apologies. I think Jason is not able to hear me. Jason, can you hear now? Jason, if you can hear me now, I'm not sure if your audio is working, but you're on mute. Jason, are you with us? Can you hear me?
Yes, I can.
You were on mute in the last 5 minutes. Apologies. And it seems like you couldn't receive my audio as well.
No, right as I was switching off on the screen sharing, I saw it said I had an unstable connection. So
Yeah, so you lost audio and mic. We
okay,
couldn't
I'm
we
sorry.
couldn't we couldn't hear it, but yeah, maybe as a I think it was only for the last 5 minutes, so it
Okay,
was that bad, but just to know.
okay. A lot of what I was saying was there on screen. So hopefully that if anybody does have any questions on that last part, then I can fill that in if they have specific questions about it.
Yeah, of course. And we also have one question, so maybe we can cover that. And
Yeah.
for others, feel free to write any questions you might have, or you can also reach out to us with some questions, and we'll try to get back to you as soon as possible. So we have one question: does Spectral Box give you a warning about slotting the holes in steel plate when the outermost bolts are more than 10 inch apart for shrinkage?
No, there is no warning about that, and that does vary. NDS actually has a limit of 5 inches on glulam members, um, which is kind of frustrating because I mean that's been done in a lot of your European connections, and they handle it a little differently, um, but you know there are ways around that, but NDS doesn't really recognize any of those options. Um, so no, there is no warning about that. Um,
That's
that's on the engineer to account for.
Yes, and also for Pro and Enterprise user, we also have ability where you can switch between regions, so you can check also Eurocode
Mhm.
and also the new Eurocode provisions, where some of these things are maybe in more detail addressed, and you can find more information about that. So I'm not sure if anyone else has any further questions. Again, apologies for the technical issues we had in the last few minutes, but as Jason mentioned, a lot of these was on screen. So if you have any additional thoughts, questions, or comments, feel free to reach out or send it in the chat. If not, we can finalize this session. Yeah, I think that will be it. Thank you everyone. Thank you, Jason. That was really great to see. And yeah, thanks everybody for coming. We'll also be presenting next month on the topic for the CLT shear walls. So please keep in touch, and we'll inform you of the right timing and topics that we'll cover. Thank you, everyone, and thanks, Jason.
Thank you. Have a good day. Bye.
Bye.